Okay, let's unpack this. Imagine the nervous system of a modern data center. Data flying everywhere, right? Calculations happening super fast.
Yeah, incredibly fast.
But what happens when the pathways connecting the brain, the processors to the information libraries, memory, storage, what happens when they get jammed?
Exactly. That's the crux of it.
That's this memory wall problem that really hit the data center world hard
Yeah.
back in the early 21st century. Processors kept getting faster,
Way faster.
but the traditional ways of moving data, they just couldn't keep up.
It was like pouring more fuel on the engine, but the fuel line itself couldn't deliver it fast enough. This gap between compute power and actually feeding it data from memory and storage, it became a really serious bottleneck.
And this wasn't just some, technical glitch in the background.
No, not at all.
It was throttling innovation. Things like big data analytics, high-performance computing, they were feeling it. Companies needed those rapid insights from their data, but the infrastructure was, struggling.
Yeah, the existing ways to connect components, traditional I/O interconnects like PCIe, they just weren't built for that scale or that speed of data movement. They were becoming the traffic jam.
Okay, so the old assumptions, like storage is always slow, memory is always fast, and right next door, those were breaking down.
Precisely. New memory tech was coming online. The sheer volume of data was exploding. The old rules didn't apply anymore. The industry kind of realized that just tweaking the existing standards, incrementally improving them, it wasn't going to cut it.
It needed something more fundamental, a real architectural shift.
Right. They needed a rethink.
So a challenge this big, it needed people to come together. And that brings us right to the focus of this deep dive. One really ambitious attempt to build a totally new kind of pathway, the Gen Z Interconnect standard.
That's the one.
So based on the sources you've shared with us, we're going to dive into the problem Gen Z aimed to solve, really explore its unique vision and architecture.
Yeah, what made it different?
Look at where it hoped to make an impact. Understand the intense competition it faced.
Which was significant.
And ultimately figure out its lasting legacy, what stuck around.
Yeah, our mission here is really to understand the why behind Gen Z. What was the driving force? What made it architecturally distinct? And why, even though it didn't become the standard itself,
Right.
its ideas are absolutely shaping the future of computing infrastructure even now.
Okay, let's jump right into that core problem then.
Yeah.
You described this data traffic jam. What specifically was causing it?
It really boiled down to two things hitting at pretty much the same time. First, this unprecedented explosion in data generation, just mountains of data.
Everywhere.
And second, an escalating demand to process that data in real time. So you have this critical imbalance. Processors were leaping ahead in speed, but the system's ability to actually move data efficiently from memory and storage to those fast processors, that lagged way behind.
That's the memory wall.
That's the essence of the memory wall, yeah.
So the compute power was there, technically, but it was often just sitting idle waiting for data.
Often, yes, or at least not working nearly as efficiently as it could. And the traditional interconnects, things designed mostly for, connecting peripheral devices using I/O protocols like PCI Express.
Like plugging in a graphics card or a network card.
Exactly. They simply couldn't handle the volume or the velocity needed for these modern data-heavy workloads. They weren't built for moving memory-like chunks of data at super high speed across the whole system.
So definite bottlenecks.
Yeah.
What kind of real-world impact did this have on applications people actually use?
Oh, significant consequences. Performance was really hindered for critical applications. Think big data analytics, high-performance scientific computing.
Stuff that needs fast results from huge data sets.
Precisely. Organizations needed to analyze massive data sets rapidly for, everything. Scientific discovery, business intelligence, you name it. And the infrastructure just wasn't keeping pace. Plus, those underlying architectural assumptions that had held for decades.
Storage is separate and slow. Memory is close and fast.
Right. Those were becoming obsolete. New memory technologies were blurring the lines. Workloads needed to treat huge data sets much more like memory.
Not like some of the you fetch from a slow disk.
Exactly. And the way established interconnects were evolving just felt too slow or maybe fundamentally misaligned with these emerging needs, especially the shift towards memory-centric computing and the desire for more flexible systems, resource disaggregation.
So tweaking wasn't enough. It needed a bigger idea, maybe a unified industry approach.
That was the thinking. It needed a more foundational change.
Which sets the stage perfectly for Gen Z. How did this big collaborative vision actually come together?
Well, the Gen Z Consortium was formally launched on October 11th, 2016. It was a direct response to these growing pressures. And what was really notable was the sheer breadth of industry players involved right from the get-go.
Like who?
Oh, companies like AMD, ARM, Cray, Dell EMC, HPE, IBM, Micron, Samsung, SK Hynix, Seagate, Xilinx. I mean, a really diverse group.
Right.
All collaborating on this common problem.
Wow. Getting that many major competitors who are usually fighting tooth and nail around the same table. That's a feat in itself.
It really is. It showed how big the problem was perceived to be.
So what was the big idea they all rallied around? What was the core vision?
Their primary vision was ambitious. Create an open, royalty-free, high-performance, memory-semantic fabric interconnect.
Okay, memory semantic. That sounds key. Let's break that down.
It absolutely was the key. This was the core paradigm shift they were aiming for. Instead of communicating using traditional I/O protocols, which, involve complex transaction layers, driver stacks in the OS, significant software overhead for every single data transfer.
A lot of baggage.
A lot of baggage.
Yeah.
Gen Z aimed to treat data access primarily as simple, fundamental memory operations, just loads and stores, like how a CPU accesses its own cache or main memory.
So making remote data access feel or act as much like local memory access as possible, cutting out all that software overhead.
Exactly. The idea was to get much, much closer to the efficiency of local memory access, but do it across a fabric connecting different components, potentially across a whole rack.
Okay, so minimize the overhead dramatically.
Right.
What else was core to the Gen Z vision? What were its tenets?
Right. Beyond just memory semantics, it had several key design principles. First, obviously, high performance. They were aiming for huge bandwidth, even hundreds of gigabytes per second, and critically low latency. They had this really aggressive target of sub 100 nanoseconds for a low-to-use operation.
Wait, sub 100 nanoseconds. Across a fabric, not just inside a chip. That's incredibly fast.
Incredibly fast. That was the goal. Then reliability. Things like features to eliminate stranded resources components, sitting idle in server support for transparently bypassing failures in the fabric, and enabling resilient data structures using hardware assistance.
Makes sense for data center scale. What else?
Security. Strong, hardware-enforced isolation between different users or applications was designed in from the start. Flexibility was huge too. The architecture was designed to support all sorts of topologies, simple point-to-point connections, daisy chains, large switched fabrics, even complex mesh networks.
Connecting anything to anything, basically.
Yeah, that was the idea. And connecting a wide range of components. CPUs of different architectures, GPUs, FPGAs, various kinds of memory, storage devices, a truly unified fabric.
Okay, a unified fabric for potentially everything in the data center. That's ambitious.
Highly ambitious. And pragmatically, they focused on compatibility. They made a key decision to leverage existing, mature physical layer technologies, the actual electrical signaling standards from PCIe and Ethernet.
The wires and signaling were already there.
Right. This made it much easier for hardware vendors to actually build components. They could focus on the new Gen Z protocol layer sitting on top of those proven PHYs. You saw companies like Amphenol developing compatible connectors based on this.
Smart move to lower the barrier to entry.
Definitely. And finally, economic benefits. The ultimate goal was better resource utilization by avoiding over-provisioning, streamlined data access which boosts performance, lower capital and operating expenses, and, crucially, faster innovation by decoupling the development cycles of processors, memory, and other components.
Okay, avoiding stranded resources, lowering costs. That loops right back to those initial data center pain points we talked about.
Exactly. The whole architecture, the protocol, it was all centered on eliminating those costly protocol translations and drastically reducing the software complexity and overhead involved in just getting data where it needed to go quickly and efficiently.
All right, the vision was definitely ambitious, comprehensive. Let's really unpack that memory semantic architecture now. How did they technically achieve this load store access across a fabric? And how did that enable things like composability?
Right. The member semantic protocol itself was the absolute core technical innovation. It defined how components would talk. Instead of block-oriented commands and heavy driver involvement like you see with, say, SAS or NVMe over PCIe.
The traditional storage way.
Exactly. Gen Z components would communicate using simple load and store operations, encapsulated in packets. This was the absolute key to hitting that aggressive sub-100 nanosecond load latency target and achieving high bandwidth.
So the interaction with the software stack, the operating system, was drastically simplified.
Massively simplified. It meant CPU cores could spend far less time bogged down in managing data movement protocols and could dedicate way more cycles to actually running the application logic. That's a huge performance win.
And it wasn't just for one type of access.
No, it was designed to be versatile. It could support the fine-grained, byte-level memory access needed for things like coherent shared memory, but also handle block access for storage devices, peer-to-peer messaging between components, and direct access to accelerators like GPUs or FPGAs, all unified under this memory semantic umbrella.
And the ultimate goal you mentioned was enabling that disaggregated and composable system, building servers virtually.
Precisely. And to make that happen, you need specific architectural components working together. First, the resource types it supported. Gen Z was fundamentally designed to be processor agnostic. It didn't care if you were plugging in a x86 CPU, an ARM chip, a power processor, or connecting a GPU or an FPGA.
Didn't matter what kind of brain it was.
Nope. And it was built to integrate diverse media tiers seamlessly. Everything from standard GRAM and NAND flash to those newer storage class memory technologies that were emerging.
Okay, so how did it handle connecting all these different types of memory and devices, especially when they have different needs, different timings?
That leads us to a really crucial innovation. The split controller model. Think about how traditional systems work. The CPU package itself contains the memory controller logic, the part that understands the intricate timing and specifics of DRAM.
Right, it's baked into the CPU.
Gen Z decoupled this. In the Gen Z world, memory modules or other memory storage devices attached to the fabric would have their own intelligent controllers on board. These media controllers would handle all the low-level media specifics like DRAM refresh timings or wear leveling algorithms for SEM, and then present a standard, abstracted Gen Z interface to the fabric.
Whoa, okay, so the intelligence about how to manage this specific memory type moved off the CPU chip and onto the memory device itself.
Exactly. This was pretty revolutionary because it allowed processors and memory technologies to evolve and be innovated upon independently. A vendor could create a brand new type of SEM, put a Gen Z media controller on it, and it could plug into the fabric and work without requiring a complete redesign of the CPU socket or its internal memory controller.
That's a really clear way to break that tight processor memory interlock.
Yeah.
Very clever. So what tied all these different components together in a larger system, like across a rack?
That would be the Gen Z switch. Switches were envisioned as absolutely central to achieving scalability and flexibility. They were the key to enabling those large, expansive fabric topologies needed for rack-scale systems.
The fabric's backbone.
Exactly. They facilitated any-to-any communication between connected components. They were essential for creating those disaggregated pools of resources, pools of memory, pools of accelerators, and enabling that dynamic composition where software could assemble systems on the fly. We even saw early prototypes like that ETRI memory pool system demonstrator, which used a Gen Z switch.
And these switches supported different connection patterns.
Yep. Point-to-point, daisy chains for simpler setups, large switched fabrics for maximum flexibility, even potentially mesh connections for redundancy and high bandwidth.
So the switches were like the central nervous system, letting resources connect anywhere they needed to.
A very good analogy. And tied closely into that was the media agnostic nature we touched on earlier. It wasn't just about the split controller hiding the details. The Gen Z fabric protocol itself was designed not to be tied to specific electrical signals or timing unique to, say, just DRAM.
How did they achieve that abstraction?
Through an abstraction layer defined in the spec called the component media structure. Essentially, each device plugged into the fabric would describe its capabilities, its attributes, its performance characteristics to the fabric manager in a standardized way.
So the fabric protocol itself was basically indifferent to whether it was talking to superfast 3M or a persistent SEM device.
Precisely. The media controller on the device handled the translation to the specific media. And then for the physical connection, remember, they made that pragmatic choice, leveraging existing physical layer technologies, reusing the PHYs from PCIe and Ethernet.
Right, speeds up to 32 gigatransfers per second initially, aiming for much higher, like 112 GTs.
Exactly. Using that existing plumbing, as you put it, really lowered the barrier for hardware vendors to get involved and start building Gen Z capable devices.
Makes sense. Using existing plumbing to build a new kind of superhighway for data. And the ultimate goal of putting all these architectural pieces together, especially when it came to memory, what was the killer app?
The flagship capability, the one that really captured the imagination, was composable memory pools. The vision was to gather vast amounts of memory, whether it was DRAM, SCM, or a mix, into large shared pools that were physically disaggregated, separate from the compute nodes, but logically accessible over the high-speed, low-latency Gen Z fabric.
Freeing memory from the confines of individual server boxes sounds potentially game-changing. What were the big benefits they saw there?
Huge potential benefits. First, it helps overcome the physical constraints, electrical power limits, cooling challenges, just sheer physical space of trying to pack ever more memory right next to hot, power-hungry CPUs.
Right, you can put the memory somewhere else where it's easier to manage.
Exactly. But even more critically, it enables truly dynamic resource allocation on demand. Instead of buying servers with fixed, often over-provisioned amounts of RAM, you could compose systems by allocating precisely the amount of memory needed from a central pool to specific compute nodes, just for the duration it's needed.
That sounds like it would dramatically improve memory utilization. No more stranded memory trapped in servers that aren't using it.
That was a primary goal, eliminating stranded memory. Companies like Smart Modular actually developed concepts for Gen Z memory modules, or ZMMs, specifically designed for these pools. And to get the high aggregate bandwidth needed to feed many processors from a shared pool, the spec defined features like 64-way barber pole interleaving across multiple Gen Z links.
Wow, okay, so instead of buying servers like fixed Lego blocks, you could buy compute bricks and memory bricks separately and assemble them virtually as needed.
That's exactly the concept. If you picture a diagram, you'd see the central switched Gen Z fabric. Connected to it are all these different nodes, compute blocks with CPUs or GPUs, specialized accelerators, maybe some storage devices, and then these big shared memory pools containing DRAM, SCM, maybe a mix.
And arrows flying everywhere across the fabric.
Right, arrows showing that low latency, memory semantic communication happening directly between components, bypassing those traditional CPU I/O bottlenecks. You'd see the split controller highlighted on the memory devices, the diversity of media types within the pools. It really paints a picture of flexible, powerful, rack-scale systems.
That really is a fundamental shift in how you'd architect and build a large-scale computing system. So with this innovative architecture laid out, where exactly did Gen Z aim to transform computing? What specific problems was it trying to solve at that higher application or system level?
Yeah, it aimed squarely at several major data center challenges that were becoming acute. First and foremost, composable disaggregated infrastructure, or CDI.
Breaking the server apart.
Pretty much. The problem was, as we've discussed, those stranded resources locked inside fixed servers, the systemic over-provisioning you had to do just in case, and the resulting lack of agility. Gen Z's solution was to enable true disaggregation, separating compute, memory, storage accelerators into independent pools, and then allowing software to dynamically compose systems from these pools on demand.
Building the right server for the job exactly when you need it.
Right. Maximizing hardware utilization, minimizing waste and over-provisioning, allowing you to scale compute resources independently from memory resources, and ultimately reducing the total cost of ownership. And that memory semantic access was absolutely key to making communication with those remote pooled resources efficient enough to be practical.
Okay, so flexibility and efficiency within the rack. What about scaling beyond just a single box or rack?
That was the second big target, rack-scale computing. Extending efficient, low-latency memory access beyond the physical confines of a single server chassis was historically very difficult with traditional technologies. Gen Z was designed right from the ground up to scale. It aimed to go seamlessly from point-to-point links within a node to spanning across a backplane, across an entire rack, or even potentially connecting multiple racks together using that same high-bandwidth, low-latency fabric.
Allowing a whole collection of resources, maybe across multiple racks, to act more like one single enormous machine.
Essentially, yes. It facilitated those large shared memory pools we talked about and enabled much finer-grained resource provisioning and sharing across the entire rack or data hall.
Okay, what about those applications that need just blindingly fast access to absolutely huge data sets, the kind that typically wouldn't fit in a normal server's memory anyway?
That's a third area. In-memory computing. The big performance bottleneck there is almost always getting those massive data sets out of slower storage tiers like SSDs or hard drives and into memory where the CPU can actually work on them.
The data movement problem again.
Exactly. Gen Z aimed to provide extremely high bandwidth, very low latency access to potentially enormous shared or disaggregated memory pools that could combine both DRAM and the faster tiers of SCM. And its native memory semantic nature, accessing data in small cache line-sized chunks, was perfectly suited for how processors actually consume data in these workloads.
Did they have any specific performance improvement numbers they were projecting for those kinds of in-memory applications?
They did, and some were quite dramatic. The sources we looked at cited potential boosts like 15 times faster in memory analytics, 20 times faster similarity searches in databases, maybe 100 times faster large-scale graph inference for AI.
Those are big numbers.
And perhaps the most staggering one mentioned was a projection of up to 8,000 times faster financial modeling applications in certain scenarios.
Wait, hang on. 8,000 times faster. That's not just an improvement. That's transformative. That's the difference between a calculation taking, I don't know, a year and finishing in about an hour, or maybe months versus minutes. What specifically was the bottleneck before that Gen Z could unlock such a massive speed up?
It is an incredible number, right? The bottleneck fundamentally was the sheer overhead and latency involved in moving that vast quantity of data over traditional I/O paths, going through the operating system storage stack, dealing with block transfers, context switches, driver interactions, all that complexity, versus accessing it directly, almost like local memory, using Gen Z's load store semantics. Gen Z aimed to completely bypass those traditional bottlenecks for data access patterns that look like memory access.
Okay, that makes the potential scale of the impact much clearer. It wasn't just faster I/O, it was a different way of accessing the data. And finally, you mentioned integrating those newer memory types.
Yes. The fourth area was storage class memory, SCM integration. These new SCM technologies, like Intel's Optane or 3D XPoint, promised performance somewhere between traditional DRAM and NAND flash SSDs. They could bridge the gap in performance and capacity, but effectively integrating them into the system hierarchy without creating new bottlenecks was a challenge.
How did Gen Z help there?
Its media-agnostic fabric was designed precisely for this. It could seamlessly integrate SCM right alongside DRAM or other media types. SCM could be attached to the fabric and presented as memory, accessible with those same low-latency memory semantics, completely avoiding the overhead of the traditional storage stack.
So SCM could be truly utilized as another tier of fast memory, not just treated as the slightly faster SSD access through the old slow paths.
Precisely. The split controller model and the media abstraction layer really simplified the adoption and effective use of these diverse memory technologies onto a single unified fabric.
Okay, it sounds like Gen Z had a really compelling vision and a technically innovative architecture aimed squarely at these major industry pain points. But as we know, history took a different turn. It didn't become the single dominant standard. What was that competitive landscape like, and how did things actually play out?
Yeah, it was definitely a time of significant ferment, a lot of activity in the interconnect space. Several different initiatives were vying for position. The most direct comparison, at least initially, is probably with PCI Express, PCIe itself.
Which was the incumbent, right?
Exactly, the established standard. We've touched on it, but it's worth hammering home the fundamental difference. PCIe is an I/O standard. It's primarily about attaching peripheral devices. It uses DMA for data transfers, it relies heavily on OS drivers, and it's built around a host-centric tree topology.
Rooted at the CPU.
Right. Gen Z, on the other hand, was designed from the ground up as a memory semantic fabric, enabling peer-to-peer communication using load store operations across a much more flexible switched or mesh topology with minimal software involvement.
So Gen Z aimed to overcome PCIe's limitations, especially that bandwidth per core bottleneck and the higher latency for memory-like accesses.
That was a key goal. Even while, as we discussed, pragmatically reusing PCI's physical layer, the electrical signaling to speed up time to market and lower the barrier to entry.
So using the same wires, potentially, but speaking a completely different, much more efficient language for moving data around.
That's a really good way to think about it. But the competition that really shaped the outcome, the most critical one, emerged from Compute Express Link, or CXL.
Ah, CXL. That's the standard we hear about constantly now.
Exactly. CXL, which had very strong early backing, particularly from Intel, initially focused on a slightly different perhaps narrower problem space. It was primarily about cache-coherent attachment within a server.
Inside the box.
Mostly, yeah. Connecting things like accelerators and enabling memory expansion, and importantly, doing it by leveraging the existing PCIe physical layer right from the start. Gen Z, remember, had that broader, more immediate vision, targeting rack-scale systems, disaggregated shared memory pools, connecting lots of diverse components, and peer-to-peer communication across the fabric.
Okay, so CXL started more as an evolutionary extension of PCIe within the server, focused on coherency there, while Gen Z was aiming for a more revolutionary rack-wide fabric for memory and more.
That captures the initial difference in scope and focus pretty well. There was also a key architectural difference in how they approached cache coherency, keeping data consistent across different caches. CXL was designed from the outset with hardware-managed cache coherency, specifically protocols like CXL.cache and CXL.mem, which makes sense for the tighter coupling inside a server.
Simpler for software.
Generally, yes. Gen Z, looking at those potentially massive rack-scale fabrics, opted for a software-managed coherency model, primarily using atomic operations. The thinking was that hardware coherency across a vast fabric could generate excessive snoop traffic, becoming a bottleneck itself.
Interesting trade-off. Hardware coherency might be simpler to program for initially, but maybe becomes a scalability problem in really large fabrics.
That was precisely the trade-off Gen Z's designers were considering. Also, initially, CXL's physical reach was limited by standard PCIe distances, fine for inside a server or maybe a short backplane connection. Gen Z was designed with longer physical links in mind from the start, even anticipating the potential use of technologies like silicon photonics for multi-rack scale connectivity eventually.
Okay, so different starting points, different approaches to coherency, different target scales initially. What were the key factors that led to the industry ultimately consolidating around CXL rather than Gen Z or maybe both coexisting?
Several factors really converged. Probably the single most significant one was that strong early backing CXL received from Intel, which was, and largely still is, the dominant CPU manufacturer.
Intel put its weight behind it.
Massively. And support also came quickly from major hyperscalers, the big cloud providers like Google, Microsoft, Meta. Intel's decision to integrate CXL support directly into their processor roadmaps provided a very clear, predictable market path for CXL adoption. That gave it huge momentum.
And Gen Z didn't have that same level of direct CPU roadmap integration from the biggest player.
No, despite its broad consortium membership, it lacked that critical integrated backing from the market-leading CPU vendor. That was a definite disadvantage in terms of driving adoption.
So having the biggest player firmly on board made a massive difference in which way the market tilted.
It undeniably shaped the landscape. Another factor was CXL's approach of leveraging the existing ubiquitous PCIe physical layer infrastructure right from version 1.0. For vendors and users, this offered an easier, more evolutionary adoption path compared to integrating what felt like a completely new standard. Even if Gen Z also reused PHYs, it felt more like an extension of something familiar.
Less disruption.
Less perceived disruption, yeah. And also, CXL's phased rollout strategy might have played a role. CXL 1.x focused on those simpler in-node use cases. Then CXL 2.0 added basic switching and memory pooling. Then CXL 3.x introduced more complex fabric features, sharing, peer-to-peer.
So it introduced the complexity gradually.
Exactly. It might have been easier for the market to digest these capabilities in stages compared to Gen Z's initial, more comprehensive vision that covered many advanced use cases right from the start.
Sometimes it's easier for the market to take steps rather than one giant leap, even if the leap is technically compelling.
I think that's often true for market adoption, yes. An evolutionary path can feel safer and less risky, even if a revolutionary approach promises more benefits eventually. And fundamentally, underlying all of this, there's a strong market preference for consolidating onto a single standard for this type of interconnect.
To avoid fragmentation.
Precisely. To ensure maximum interoperability between components from different vendors and reduce complexity for system builders and users. Nobody wanted multiple competing, incompatible memory fabrics.
So how did this competition between Gen Z and CXL formally resolve itself? Did they just compete until one faded?
Well, they initially recognized there might be potential complementarity. They actually signed a Memorandum of Understanding in MU back in 2020. The stated intent was to explore collaboration and potential interoperability between the two standards.
Trying to find a way to work together.
That was the idea, but ultimately the market momentum just shifted too heavily towards CXL. So in November 2021, the members of the Gen Z consortium voted to transfer all of their specifications, their intellectual property, patents, assets, everything, over to the CXL consortium.
Wow, okay. So they basically merged the efforts under the CXL banner.
Effectively, yes. That transfer was finalized in early 2022, and CXL became the single unified industry standard effort for these kinds of coherent memory semantic interconnects moving forward.
So rather than competing indefinitely or fragmenting the market, they consolidated. Were there any other standards in this space that met a similar fate?
Yes, there was another significant effort called OpenKPI. It was backed primarily by IBM, AMD, and Xilinx, and it also targeted coherent acceleration and memory attachment, overlapping significantly with both Gen Z and CXL.
Another contender.
Right. And like Gen Z, it faced challenges gaining broad market share against the CXL momentum and felt the strong industry pressure for consolidation. Ultimately, OpenCAPI also transferred its assets and specifications to the CXL consortium in August 2022.
So CXL basically absorbed the work and membership of both Gen Z and OpenKPI.
That's right. So those interconnect wars of that period, which really did risk fragmenting the market and slowing down progress, ended with CXL emerging as the standard bearer, incorporating ideas and technologies from the others.
That consolidation provided much-needed clarity for everyone involved, vendors and users alike. Those comparative tables summarizing the features really highlight the different initial approaches and how they ultimately converged under CXL.
Exactly.
Okay, so given that Gen Z as an independent standard didn't ultimately make it to widespread adoption, what is its lasting impact? What did it really contribute to the future of computing? Does it have a legacy?
This is where the story gets really interesting and I think quite positive in the end. While Gen Z didn't achieve market dominance under its own name, its legacy is incredibly significant and highly influential. It really was a true pioneer. It championed concepts that are now absolutely foundational to the advanced computing technologies being developed and deployed today.
So even though the Gen Z brand isn't on the box, its ideas are inside. What were those core pioneering concepts that lived on?
The most important ones are those core ideas we discussed. The whole concept of a memory semantic fabric doing load store over a network, the powerful vision for true disaggregation and composability of resources, the fundamental goal of breaking the processor memory interlock to allow independent innovation, the ambition of having a unified fabric for diverse components, and the critical emphasis on scalability from the node all the way to the rack and beyond.
These weren't just vague ideas Gen Z talked about.
Not at all. The Gen Z consortium didn't just talk about these things. They developed incredibly detailed specifications, they fostered an ecosystem, they built multi-vendor proof-of-concept hardware demonstrating these exact ideas years ago. They effectively forced the industry to stop and fundamentally rethink data center system architecture.
And you're saying these specific ideas, maybe even the technical work, directly influenced CXL as it evolved?
Absolutely. You can literally see Gen Z's fingerprints all over the later CXL specifications. CXL 2.0, for example, explicitly introduced memory pooling that was a concept absolutely central to Gen Z's initial vision from day one.
CXL adopted pooling.
Right. And then CXL 3.0 and the recent 3.1 specifications have significantly expanded on fabric capabilities. They've added features like much more complex fabric topologies beyond simple trees, support for peer-to-peer communication directly between devices, sophisticated memory sharing across multiple compute nodes, and advanced fabric management APIs.
Features that sound remarkably alike.
Features that map directly onto the advanced disaggregation and composability goals that Gen Z was championing right from the beginning. In fact, the extensive work Gen Z did specifically on defining fabric management was acknowledged as a particularly valuable contribution that was absorbed and built upon by the CXL consortium.
Wow. So it's not really accurate to just say CXL won. It's more like CXL became the vessel that carried forward not only its own initial ideas, but also key parts of the Gen Z vision and technical groundwork.
That's a very accurate way to put it. The fundamental problems Gen Z identified, the memory wall, stranded resources, the need for flexibility, are still critical challenges. And CXL is now the standard vehicle for realizing much of that original Gen Z vision, built in part on the technical foundation that Gen Z helped explore, define, and prove out. Gen Z truly accelerated the industry's journey towards these advanced memory fabric solutions.
So despite the outcome for Gen Z as an independent standard, The actual work done by the Gen Z consortium wasn't wasted effort at all.
Far, far from it. They developed comprehensive, open specifications. The Core Spec 1.0 released back in 2018 was a major piece of work. They successfully built a large and active ecosystem with over 60 member companies seriously engaged. They demonstrated real multi-vendor interoperability at major industry showcases like the Flash Memory Summit and supercomputing conferences.
Showing it could actually work.
Exactly. And they conducted substantial educational outreach, publishing white papers, giving presentations that significantly raised awareness across the entire industry about the need for and the potential benefits of memory-centric computing and disaggregated architectures. They helped educate the market.
They did the crucial foundational work and helped prepare the ground for these ideas to take root, even if it ended up being under a different banner. Okay, so summing up, the key reasons the independent Gen Z standard didn't ultimately succeed were things like that formidable CXL competition, especially with Intel's strong backing.
Right.
The market's understandable preference for converging on a single standard to avoid chaos.
Yep, consolidation was key.
And maybe also the perception that Gen Z's initial scope felt more complex or its timeline less certain compared to CXL's more gradual phased rollout.
I think that's a fair summary of the complex market dynamics that were at play during that time.
So the final perspective seems really clear then. Gen Z wasn't a failure, not at all. It was actually a highly influential pioneer that fundamentally shaped the future direction of data center interconnects and memory systems.
Absolutely. It pushed the boundaries hard. It demonstrated what was technically possible with a truly memory semantic fabric. And its core ideas, its architectural DNA, are now being implemented and deployed at scale within the dominant CXL standard. Gen Z was a crucial catalyst and a truly foundational contributor to the next generation of computing infrastructure we're building today.
It's a powerful example, isn't it? That the impact of innovation isn't solely measured by whether your standard wins the market battle, but by how profoundly it influences the direction the entire industry ultimately moves.
Couldn't agree more.
So that was our deep dive into the story of Gen Z. We started by exploring that critical challenge facing data centers, the memory wall. This bottleneck caused by the data explosion, overwhelming traditional ways of moving data.
A problem demanding a new solution.
We saw how the Gen Z consortium emerged with a really bold, arguably revolutionary vision for a memory semantic fabric, an architecture designed to fundamentally change how compute, memory, and accelerators talk to each other.
Enabling capabilities like true disaggregation and wrap-scale computing.
We delved into its innovative architecture, unpacking things like the split controller model and the concept of composable memory pools, and then we navigated that intense competitive landscape, understanding how CXL gained prominence and why the industry made that strategic move to consolidate standards under its banner.
And here's where I think it gets really interesting when you step back. While Gen Z didn't ultimately become the independent standard flying its own flag, its core ideas, its vision, they didn't just vanish.
Wow.
In fact, they were absolutely instrumental in shaping the very standard CXL that is now driving the future of memory-centric computing forward. CXL directly incorporated Gen Z's foundational vision for pooling resources, sharing memory, and building large-scale flexible fabrics. Gen Z really did accelerate the industry's transition towards these next-generation architectures.
So what does this whole story mean for you, listening in? Well, it means that the fundamental ideas and technologies powering the clouds, the AI platforms, the supercomputers of today and tomorrow stand firmly on the shoulders of the pioneering work done by groups like the Gen Z Consortium.
Yeah, it's built on that foundation.
It shows us that innovation isn't always a straight-line victory march. Sometimes, the most impactful contribution a new idea or standard can make is to light the way, to provide the essential blueprints and proof points that others will ultimately use to build the final structure.
It's a great point. And maybe here's a final thought for you to mull over as we wrap up. In a technology landscape like this, where standards often compete fiercely, where market forces lead to consolidation, how does the industry ensure that the truly groundbreaking ideas, the most innovative concepts, regardless of which consortium or which company initially champions them, actually find their way into the widely adopted technologies that ultimately define the future for all of us?
How do we make sure the best ideas win, even if the original standard doesn't? That's a fascinating question to ponder.